class. So we have James and Sergey from the Dartmouth College. They're going to talk about exploiting the hardworking dwarf.
Hello, I'm Sergey Bratus. I am a sort of a professor at Dartmouth College. You can see the logo on the screen. This is one of the oldest colleges in America, founded in 1769. So, have some respect for the ancient venerable. James is a student in our lab, and we're going to talk to you about an exciting discovery we made when looking at something as basic and as hopefully well known to this community as the ELF binary format and the accompanying format called DWARF. When you want to close that door, there is a technical detail. All right, thank you. So, and here's what this is about. You take any program that you compile with GCC, and you get exception handling information included with the object file. It will make its way into the final binary or shared object. So what that means is there is a chunk of data in each and every GCC compiled executable that contains what is known as DWARF information. Now, DWARF associates very firmly with debugging, right? In fact, everyone we talked to pretty much, told us, yes, this is debugging. What about? What about it? This is not about debugging at all. This is about exception handling. When you strip your executable, it's still there. Now, what this DWARF information is actually bytecode. The format for unwinding the frames, for unwinding the stack when you do exception handling, is quite complex. So it turns out that what you actually put in there is bytecode that generates this information on the fly as needed for your stack unwinding exception handling routine. The interesting part about this is that it's so forward-looking that the bytecode is Turing-complete. So every GCC compiled executable carries a program, and when loaded in memory, that program carries around a virtual machine for interpreting that bytecode. So if you look at it from the point of view of software engineering, this is great because you can accommodate pretty much any future stack unwinding exception handling routine. When you look at it from the hacking point of view, you see a virtual machine that interprets code that's nothing like the basic code, that is probably not looked at any antivirus in existence. And it allows you to call functions, make system calls. Well, actually, one function and one system call is really easy. After that, it gets a little bit more tricky. And it's a perfect place to put Trojan logic. We're working on making this a payload for an export as well. So let's look at DWARF. I'm a huge fan of The Lord of the Rings, so not the movie, the book, but please excuse the images of dwarves, elves, and so on. It's a sort of a private joke. How many Lord of the Rings fans in there? Man, we're not in Kansas anymore, right? In the US, you would expect a much better penetration rate of Tolkienist fandom. among hackers, but thank you. Anyhow, we did actually have a title slide in Dwarvish rules, as used in the book and the movie. So these are the things to know about the dwarf bytecode. We're going to go into them in detail, and in the end, we'll release a tool for actually writing just about any program into that dwarf bytecode. And James, who wrote most of the tools, actually even wrote an Emacs mode for your convenience. So the thing about dwarf then is that the exception handling bytecode is specifically designed to examine the memory of the program. It's specifically designed to restore registers, because the whole point of having that exception handling information is that you can restore registers stored in stack frames. And it's meant to influence the flow of the program. So this is the best language ever in which you want to write the next program. So we have to quote prior art. This sort of an idea of using an army of dwarfs to take over the world has been amply explored in the Nordic sagas, the Elder Edda. Richard Wagner has this in his Rheingold, and of course John Ronald Reuel Tolkien has, if you remember, the Rings of Power, the largest segment, well, not quite the largest, but a significant segment belongs to the dwarf. You make them work for you, you take over the world in rather unnoticeable ways. So this is the story of the two friendly formats, both named, for the races of Middle-earth, Elf and Dwarf. Dwarf stands for debugging with attributed records, and it's clearly a constructed name. But forget debugging. This very same format is used for exception handling. Exception handling is a much bigger deal.
All right, so hopefully most of you will have some familiarity with ELF. It's just a binary format with lots of sections. So the ones we're most concerned with here are EH frame header, and GC accept table. So you don't need to know anything about them yet. I'll get into all the details, but just keep that in mind. And it just looks like nonsense, but we'll get into how we can actually read that. So at runtime, we're going to be most interested in libgcc and libstandard C++. And again, the sections that I mentioned.
And again, these would be loaded for into any process image if you're dealing with the GC compiler.
All right. So do you guys want to see a demo? All right. So I have a program here, and it doesn't really do much. If I give it some input it's not expecting, like say foobar, it just throws an exception. So it's a stupid little program. There's nothing malicious about it. There's no exec function or anything in it. It's pointless, but it's pretty harmless. Now I have a slightly modified version of this program. But let's take a look at the disassembly. Remember, obj dump is going to show not just the text section, but PLT and C4s, etc. Anything that can be interpreted as object code. So if we look at the disassembly of the original program, sorry. Not trying to pull that much of a cheap one on you. So if we look at the two disassemblies, we notice that, I'm sorry, hang on a sec. assemblies. The only thing that differs is the name. So they should be executing exactly the same code, right? So let's just pretend for a demo that this is some important daemon that we want to run as setuid. And there's nothing important about setuid for this demo, but it just makes it clearer what's going on. So we're going to make our modified program setuid. So if I run it, it should be harmless, right? So in normal usage, it functions exactly the same way. Let's try giving it the input it didn't expect again. And now I'm root. So we got a shell and something that looked as though it should be doing exactly the same thing. So let's dig deeper and see what actually is going on there. Sergey came to me with this crazy idea. He said, there's this format called DWARF. I don't know much about it. Very few people know much about it. But I think there's something interesting going on there. So then I started to take a look at it. So why should you be interested in this? We've got an unexplored computational model. It's in any C++ program or program linking to a C++ library. And this isn't just C++. C++ is what I've been working with, but it's any of the GCC languages that use any form of exception handling. So Java subcompiled with GCJ will do the same thing. So there's potentially a pretty large attack surface.
That will actually be important later because we will see what happens to the EH frame in virtual machine implementations.
So this is a fresh code hiding vector, so it may pass unnoticed for a while. And one of the interesting things is that we're playing entirely within the rules here. We're not doing anything illegal with exception handling information. We're using a system within its rules with the structures that it was built to include, and not relying on any vulnerabilities per se, any bugs that might be fixed.
It is just that the system was meant to do so damn much.
So it's interesting that we found a very powerful computation environment in a place that most people aren't going to think of as a computation environment.
This is literally a different assembly language, which has nothing to do with the native assembly language, and is wonderfully portable, as long as your exception handling libraries are compatible.
So let's take a look at what this is and what it isn't. So it's a Turing-complete computational model, as we've discussed. I've just demonstrated a backdoor Trojan. There's a binary extraction manipulation tool that I built that I'll discuss in a little bit. This isn't really a weaponized exploit yet. We're making some progress towards that goal. We've been talking with some smart people like Rodrigo, but haven't quite gotten there yet. And just to be clear, this isn't SEH overriding. Windows SEH overriding is very common. This is completely different. This is just Unix exceptions.
And this has nothing to do with storing anything on the stack.
So one of the interesting things here is that we're sort of on the edge of a system. And the error handling paths of a system are often not tested well, not validated well. People tend to look more at the normal operation of a program and make sure that it works properly in the normal operation. And the program, the demo that I showed, it works just fine in normal operation. As long as it's receiving expected input, doesn't throw any exceptions, then everything proceeds as normal. So it's got a very nice, clean trigger mechanism.
Moreover, your behavioral hits or intrusion detection systems will probably ignore error paths.
So most people don't look at DWARF much, don't touch DWARF. I'm curious, how many people in this room are already familiar with the DWARF format? So one gentleman, two. I was at an interview at a U.S. government-funded research lab and mentioned this research, and one of the people said, "Oh, DWARF." And so the other fellow said to him, "Oh, do you actually know anything about it?" And he said, "No, nobody touches DWARF." So it's not something that is very